Okay, so welcome everybody to round 2 of the Algebra, Particles, and Quantum Theory seminar series. I'm happy to introduce to you tonight's speaker, Glaser. Is currently a postdoc in the mathematical physics group at the University of Vienna. They specialize in quantum gravity in general, and more specifically in causal set theory and non-commutative geometry. Completed a PhD on endeavors in discrete Lorentzian geometry at the Niels Bohr Institute in Copenhagen under the supervision of Jan Ambjorn, winning the Bergman-Wheeler Thesis Prize. After this, they went on to postdoctoral positions at the University of Nottingham, Radboud University, and now University of Vienna, upon winning both the Lise Meitner and Marie Curie fellowships. Elle is an active participant in public outreach, including being invited as a guest to appear with Bill Nye the Science Guy. And today, Elle will be telling us about recent work that stems from a paper they wrote not so long ago, reconstructing manifolds from truncations of spectral triples. Now, before I begin, I would like to emphasize that everybody who showed up here today is here to learn. And so I'd hope that everyone feels comfortable enough to raise their hand and ask a question throughout the talk if they have one. If you accidentally ask a silly question, it is not a big deal. You just brush yourself off and try again next time. I would especially like to encourage questions from graduate students, upper level undergraduates, and postdocs. So Elle, anytime you're ready.
Yeah. Well, thank you very much. I'm feeling a little bit embarrassed after the introduction. I'm sure you expect a very entertaining talk now. I don't know if I can deliver that, but I'm going to do my best. Also, please ask questions. I'm going to be writing on my slides. So if we get distracted, I can throw in another slide just for writing if we want to change topic slightly from what I have planned. Also, Cohl kindly said that it's recent work. I think the paper is from 2019 or 2020, so it's a little bit older, but I'm actually going to talk about the ongoing work of extending what I've done in the past with Abelstern, and Cohl sent around the reference. I forgot to write it down and I can't remember it right now, but very lovely work on, well, the original work was visualizing truncated spectral triples. And today I'm talking about imaging finite spectral triples. So there's a very slight difference between the two concepts. So for my talk today, I'm going to assume that not everyone here knows what a spectral triple is. So I will try to motivate why I'm looking at spectral triples and give a little bit of an introduction. Then I'll talk about how we made a picture of spectral triples and how it works for finite spectral triples in particular. I'll be talking a little bit about the computer algorithm that we used, the logic of that. And then in the end, I will show some pictures that actually no one but me has seen yet, because they are for the paper that I hoped to have finished in February, but now teaching has started up again and I'm going a little bit slower with it than I planned. But let's see where we go. And yes, please ask questions. And I disagree with Cohl. There are no silly questions. I'm sure if one of you asks something, someone else will wonder the same thing. Probably I haven't explained it clear enough. So let's go. Well, first, the motivation. Why do we think spectral triples are an interesting idea? And it starts out with spectral theory, which is the famous question by Mike Kutch. Can we hear the shape of a drum? If I'm just given the sounds that a drum produces, can I hear what shape my drum has? So if I want to look at that mathematically, it's actually an eigenvalue problem. So if I have a membrane omega with a fixed boundary gamma, then I can write the eigenvalue problem on this membrane as 1/2 omega squared psi n. So I'm sure you're all at least familiar with eigenvalue problem. And holding it fixed on the boundary just means our function is fixed on the boundary gamma. Now, say I have two different membranes, omega 1 and omega 2. with boundaries gamma 1 and gamma 2 with the same spectrum, lambda n. Now, if they have the same spectrum, are they necessarily the same up to symmetry transformations? Like, obviously, if I have a drum and I'm just turning it around, it'll still be the same drum and make the same sounds. So is it up to those transformations the same drum? It turns out that's not the case. And I'm going to try and draw the example. I probably should have copied that example from onto the slide. But basically, if we assume a square grid, then this little drum, so these are 2 length pieces, this is one, and this little drum, so here each of these are 1 length step. These 2 drums actually have the same spectrum. So just knowing the spectrum is not enough to know what the drum sounds like. Now, spectral triples are kind of an extension of that, saying, okay, maybe just the spectrum is not enough. Maybe we need the spectrum and a little bit more. And that little bit more, at least in spectral triples, is having the algebra, so to say, hand-wavily speaking, the eigenfunctions. And if we have the eigenfunctions, we need the Hilbert space those functions are acting on. So in general, a spectral triple is given as an algebra of functions, a Hilbert space, and a Dirac operator. Dirac operator is for a spin manifold spectral triple. There is a different way to do it for just a Riemannian manifold, but I'll always assume that I have a spin manifold because in the end I'm interested in physics, which means that I'd like to have particles, so I'll need spin. Now, my spectral triple has a bunch of axioms associated to it, that is, things that the algebra and the Hilbert space and the Dirac operator need to satisfy. If they do satisfy this for a commutative algebra, we can actually see that it's the same information that we would have if now let me get the exact terms correct. If I have a compact smooth manifold, I could write the compact smooth manifold as the topological space with the metric, or I can write a spectral triple. And by Gelfand's theorem, it's the same information. So the axioms that need to be satisfied are: I need a faithful action of my algebra. So a faithful action of my algebra on the Hilbert space. So I need a representation. Often kind of drops under the table that we have to have a particular representation, but in some edge cases, it actually becomes very important. And often we want to look at not just a spectral triple, but a real spectral triple. Then we'd like the Hilbert space to be a bimodule over the algebra. So H is a bimodule. Over the algebra. So that means it has a left and a right action. And in most cases that I'm actually interested in, that just means that I can left multiply my algebra elements to the Hilbert space elements and right multiply them to the Hilbert space elements, because everything will turn out to be matrices. That happens in 2 slides. Next slide will be an example. And then there's a bunch of regularity conditions, a bunch of conditions about compactness, and a bunch of conditions that tell you about the dimension. I'm gonna leave these all aside for the moment. If you are interested in them, either ask now or better look up the papers, because they will explain it much better than I can. The one condition that I'm actually going to talk about is the first order condition. The first order condition is what makes sure that your Dirac operator actually acts as a derivative operator, as a first order derivative. And what's a first order condition if we're writing it out, says is if I'm commuting my Dirac operator with right representation of an algebra element, then this commutes with a left representation of any other algebra element. Or how I like to hand-wavily put it for myself, it's my Dirac operator has a part that acts on the Hilbert space from the right and a part that acts on the Hilbert space from the left. It has no part that acts at the same time from the right and the left. So we can always only come from one side at the Hilbert space. So this is an abstract spectral triple. We'd like an example of maybe a simple spectral triple to understand this better. And let's start with something really simple, which is really just the, yes, John?
Hi, you mean equals 0 on the previous slide?
Oh, did I? Okay, sorry. Yes, I forgot an equal 0. Very good, thank you. First order condition, this needs to be equal to 0.
Sorry, did you give a motivation for where the first order condition comes from?
Yes. Sorry, the slides always take a moment when I flip them around, so there'll always be a bit delay between them. The first order condition basically means that it's a first order derivative.
Okay.
So that's what it does. It means we're only.
Yeah, if you had it acting on both sides at the same time, then sure. Okay.
Yeah, so good. Now, a simple example for a commutative spectral triple is actually we can write the circle as a spectral triple. And for the circle as a spectral triple, our algebra is actually a single unitary operator that acts on the space of L2 functions on the circle. And so it's a unitary function. And so it's a unitary function. And my Dirac operator obviously will need to be self-adjoint. So the unitary function, does this one come from? I think this comes from the first order condition. Sorry. So I think from the first order condition, if we pluck it apart, we see that this will have to happen, which is equivalent. So u star du is the same as d plus 1. So that means that d, if we have an eigenstate of d with eigenvalue lambda and en, then d acting on u times the eigenstate gives us lambda n plus 1 u en. So basically by acting with the unitary operator, we can get all of the possible eigenvalues, and just the eigenvalues are how many powers of the unitary we have. So we can generate all of the algebra elements for our states just as a power series of u. And this is, as a spectral triple, the smooth function on the circle acting on L2 on the circle, and our Dirac operator is actually really just the derivative. So this is the really simple example of just a commutative circle as a spectral triple. Now, of course, most of the time when we're talking about spectral triples, we're actually talking about non-commutative geometry. So how do we make up a non-commutative geometry? Since I will be talking about finite non-commutative geometries, but there are also infinite non-commutative geometries. And one easy example to do that is actually to make up a torus. So a commutative torus is pretty simple. We just take two commutative circles and can make u star, v star. We now have two generators. It's two circles together gives us a torus. But we can then make it non-commutative. By simply introducing a phase. So uv is equal to theta vu, where the phase theta is e to the 2 pi I theta, customarily written. And if we do that, we end up with a non-commutative torus. And now I found the mistake in my slides that I was searching earlier and couldn't find, and I can't remember how to do it right. This is not the right, this is the commutative spectral triple for torus. I knew that I should write down so this is for commutative torus. And so this is the commutative torus, and so this is not a pi, this is the T for torus. Sigma J are the Pauli matrices. And I forgot to write down the spectral triple for the non-commutative torus, I'm sorry. Well, okay, so we have a commutative torus. Okay, we'll just move past that. Because there will be another example of a more interesting fuzzy space next, which will be the fuzzy sphere, which is actually what I'm going to paint a picture of. But before I can talk about the fuzzy sphere, I will need to talk about what is a fuzzy space, or what do I understand as a fuzzy space. I have to make very clear this is what I like to call a fuzzy space. People call different things fuzzy spaces. Yes, Howard?
Unmute. Oh, sorry. The question was on. Oh, I guess okay. The question was on the previous slide. There was a sigma. I realize it's just the commutative torus, but what was this sigma to the j? It looks like in the spectrum.
Oh, okay. No, I said it as an aside. These are the Pauli matrices.
Ah, okay. So it is just what one might have thought. Okay.
Yes, it's very strict. Yeah.
Okay, and you have 3 Pauli matrices there, or
exactly? You have 3 Pauli matrices
okay.
for 2 torus.
Thanks.
So, no problem. Thanks for asking. Always good to clarify. Good. So, okay, so fuzzy spaces, I like to call fuzzy spaces what actually are real matrix spectral triples. You should always ask someone who tells you they are doing fuzzy spaces what exactly they are doing, because fuzzy spaces might actually be just smeared out spaces. It might be based on string theory. It might be based on matrix geometry. It might be based on matrix geometry coming from string theory, or it might be someone working on spectral triples. So always check what exact fuzzy space someone has in mind. Now, for me, fuzzy space are really just a matrix algebra. So quite nice and simple and well behaved. Just the star algebra of n by n dimensional complex matrices. And they are acting on a Hilbert space, which is a Clifford module V tensored with MNC. So V is a PQ Clifford module. So I think it's pretty obvious to consider how matrices would act on a Hilbert space that is something tensored with matrices. We can just take our matrix and multiply it to the left, from the left or from the right into our Hilbert space matrices. So that's pretty nice. Why are we acting the complicated part of the Clifford module? It's because the Clifford module is what we need if we want to do a real spectral triple, which gives us a few extra dimensions. One is the KO dimension, which we need for all kinds of KK theory stuff. It tells us a lot about how different things should be commuting. And in theory, I could show a nice table of pluses, plus ones and minus ones to tell you what commutes or anti-commutes. In practice, I will just tell you that it does or does not, and forget about the minus one. So the KO dimension is given as Q minus P mod 8. This is checkerboard of Clifford matrices, sometimes called. We have a chirality, the chirality operator. So chirality acting on an element of the Hilbert space. Element of the Hilbert space, so V cross M, is just the chirality on the Clifford module times M. So it does not do anything to the matrix part of our Hilbert space, and it just multiplies the Clifford, the part of the Clifford module with the chirality operator on the Clifford module. And then the real structure, J, will be acting on V cross M, C, V cross M star. And C is charge conjugation. On our Clifford module. So the structure, the place where I always look it up is the lovely paper by John Barrett about matrix geometries. And the real structure, what it actually does for us is that it maps a Hilbert space element to another Hilbert space element so that JUJV is the same as U comma V. And what that also means is that if I have a right action of the algebra element, and then I do real structure, left action of the algebra element, complex conjugate, inverse of the real structure. So basically, the real structure allows me to define a right action from the left action or vice versa. So it connects the two actions of our algebra. And this is the structure for a real finite matrix spectral triple or a fuzzy space. Now you can do all kinds of fun things with fuzzy spaces like that, for example, computer simulations, because having this structure actually restricts your Dirac operator quite a bit. So if I have a Dirac operator on such a real spectral triple, well, as a Dirac operator, it should always be self-adjoint. The Dirac operator needs to commute or anti-commute with chirality. If it should commute or anti-commute, that's one of those signs that depends on KO dimension. It needs to commute or anti-commute with the real structure. Guess what? If it commutes or anti-commutes also depends on the KO dimension of my space. And the sign for J and the sign for gamma are in most KO dimensions not the same. So each of these signs is set by the KO dimension, but they are independent. And then, as I was saying before, my Dirac operator should obey the first order condition. So I have that it's a Dirac right action of an algebra element with the left action of another algebra element is 0. And if you have all of these conditions on the Dirac and put it together, it turns out your Dirac operator actually is allowed to do only very few things. Because what your Dirac operator now can do is it can multiply the part that is part of the Clifford algebra with an omega, where omega is, well, I should not use the same index. So I just write it like this. The omega can be any product of your Clifford algebra elements, but only products that, so omega can be products of Clifford algebra elements, but if the product of the Clifford algebra elements is self-adjoint, then my matrices Ki and Ki star need to be self-adjoint. If it's anti-self-adjoint, then the matrices need to be anti-self-adjoint. And Ki and Ki star are just matrices. So we can multiply from the left with a matrix and from the right with a matrix. Epsilon prime is once again a sign that depends on which KO dimension we're in. So your Dirac operator really is given by products of gamma matrices and a bunch of matrices. And we, for example, yes, Howard?
Yes. Is Ki star actually the adjoint matrix, or is it just some other matrix?
No, it's actually the adjoint matrix, yes.
Okay, thanks. That's
yes, that's very good question. Yeah. No, so you basically only have some matrices, and if you've set your Clifford module, you can write out all possible omega I. There's a finite number of them that's linearly independent. So there's a fixed number of terms and a fixed number of matrices that you can allow. And so all geometries of that type PQ will be given in terms of these matrices. So let's look at an example of that at one particular type of geometry, which will turn out to be the fuzzy sphere in a certain restriction. So we're going to look at PQ geometry, which are 1-3 geometries. And I did not want to change my pen. So I'm looking at 1-3 geometry because 1-3 geometry means that the KO dimension is the same as for 2-sphere. Some of you maybe know the Grosser-Snyder. Dirac operator for a fuzzy sphere. That one uses a 0-2 Clifford geometry. But 0-2 does not, 0-2 has Clifford dimension, has KO dimension 8, and 1-3 has KO dimension 2, so the same as for the sphere, well, this does not. So that's why this is maybe not ideal, although it works the same, but we're going to do the example of the 1-3 sphere. So again, my algebra in general are, sorry, I used a different notation before, n by n complex matrices. And since we're going to go for the sphere, one very natural basis might be the irreducible representations of SU2 up to spin J 1/2 n minus 1. So that would be one possible basis, but of course I'm not restricted. The Hilbert space, in this case, is C4 cross MNC. And so the most general Dirac operator that I can have acting on the space is actually given as, and this is going to be a little bit of writing. So I'm summing over j smaller than k. So summing over j and k, j smaller than k from 1 to 3. Gamma 0, my 1, 3 Clifford module has gamma 0 matrix. So gamma j, gamma k, tensor. Commutator with ljk, where ljk is minus ljk star. So this is anti-Hermitian matrices. Plus there's only one term, gamma 1, gamma 2, gamma 3, which comes with an anti-commutator of a Hermitian matrix. Plus a single term with gamma 0 matrix. H0 anti-commutator. Plus a sum I equal 1, 2, 3, gamma 1, gamma I, anti-commutator Li. So all the L's are anti-Hermitian matrices, all the H are Hermitian matrices. And this is the most general form for the Dirac operator. Now, in general, these could be any matrices, but if we want to restrict it to the fuzzy sphere, to the Dirac operator for the sphere, then what happens is all of these terms disappear. This is actually just the identity, and JK are so LJK are just the Lie algebra generators of SO3. And then that is the Dirac operator acting on the fuzzy sphere, which means that our matrix geometry is now a fuzzy sphere. So that's a restriction. But of course, the class of all 1-3 geometries is wider and contains more different possible geometries. There's a lot more freedom in there than we get in this particular restriction. So John Barrett and I have explored doing path integrals over fuzzy spaces by varying over these matrices. Also, a student of John, Mauro D'Arcangelo, wrote a wonderful PhD thesis about it, which I think is on the archive, where he extended our work even more. But what I turn to from this is the question of how can I, if I get the general geometry, how can I understand what kind of thing I'm seeing right now? Which turned out to be not quite as simple. So we started visualization actually with the truncated spectral triple for a sphere. Now I've extended it to the fuzzy sphere, and I'll show you pictures for the deformed fuzzy sphere, which is the first slow step towards making pictures of more general spectral triples. Now, if I'm making pictures of spectral triples, so far I've talked to you about the algebra and the Hilbert space. I haven't really talked about how we could reconstruct maybe geometric notions from a spectral triple very much. So let's do that next. Let's talk about when you have a spectral triple, what is the distance on a spectral triple? Now, the definition for the distance on a spectral triple by Alan Kohn is the distance between two states omega 1 and omega 2 is the supremum of A over all algebra elements for the norm omega 1 A minus omega 2 of A under the condition that the norm of D comma A smaller or equal than 1. So this is kind of This is kind of the Lifshitz condition. And this is just the norm, and norm as a supremum over distances is fairly well known. So one possible example for thinking about this is if we're going back to just functions on space. So say I've got my space, the real line, and I have a point x and a point y. And now I want to know the distance between the point x and y. But I want to find out the distance between point x and point y using functions. Well, speaking in function language, the function that tells me the distance between point x and point y is actually really just a linear function. So the linear function f of x equal to x, the value at point x minus the value at point y, is really just the distance between the point. This picture is kind of yeah. So that's the intuitive picture about how that works. So this is constant spectral distance, and this is from which we started for making pictures of a spectral triple. We know we can make we can get the distance between states, but well, it's not quite that easy. We actually need to think a little bit. So I want to do numerics. I want to use numerical methods to get a picture of a spectral triple by using the distance between states on the spectral triple. But what kind of states? Well, we decided that the right kind of state to use are states of a small dispersion. So try to find states that are as close as possible to points means a small dispersion, which means I need to define what is the dispersion on my spectral triple. I will do that for you in a moment. But the basic idea was, let's find states that are as close to points as we can make them. It's a fuzzy space, so there are no exact points. And then if we have the states, if we have these points, let's just use the distance between the points. And there's actually an algorithm in computer science to go from, we have distances between points, show me if we embed that into a Riemannian space, what the space looks like. And it turns out that basically worked straight away for what we wanted to do. But if we want to do that, there's a few questions we'll need to, a few more questions we'll need to be clear about. I'll need to tell you what are my states, what is a small dispersion. But then I also need to consider which algebra elements. How do I optimize over all algebra elements? And I need to figure out what are my states of small dispersion. So now the easier part are actually the algebra elements, because it is an algebra. I can just use a linear combination. I can pick any basis AI of my algebra elements, and then just have a constant CI, and I can minimize over my function CI. So let me write before I talk. It's always better. So to get this is distance between the, so this is the norm between the algebra elements. Once we've put in the linear combination for the algebra elements. So I can really just minimize over this, of course, with the side constraint that the commutator is smaller or equal to 1. That works out pretty well, and I can pick whatever basis I like. It turns out it works particularly well if at the basis I start out with the matrices that are in the Dirac operator and take generate all possible linearly independent the power set of those. But it works just as well if I do the most well, it doesn't work quite as well because it's a larger space to go over, but it does work to just say, let's take the matrices where only a single element is not 0. And I can take the set of all of those n by n matrices with just a single non-zero element and use them as a basis. That's a lot more and it makes the computer slower, but it still works. And then the second part we need to do is minimize our dispersion. So the dispersion, again, we need the same constraint. And what is my dispersion? So we can define, again, very similar to how we define the distance, we can define a dispersion. So the supremum over all algebra elements. And then, so the dispersion of the state omega is omega a star a acting on omega minus omega a omega squared. So a squared acting on omega minus the squared of a acting on omega. Really very much like we'd think of a dispersion or a variance. And again, we have the additional condition that the commutator is smaller or equal to 1. This is a good definition in a theoretical case. This should work very well. If we're doing it on the computer, we actually run into 2 problems. The first is that this is a non-convex double optimization. So clearly, I can easily calculate the dispersion of a given state omega by optimizing over A. No problem with that. My computer is happy doing that. Where we start running into problems is I'm looking for states omega that have a small dispersion. That means I'm trying to minimize omega, but I also need to find the supremum over all A for each omega. That's a double optimization problem. I'm trying to optimize one thing in condition to another. And that is where the computer starts going, nope. There's no really good algorithms for that. So we'll need to figure out some kind of ad hoc heuristic that is well enough that works for this. And for the things on fuzzy spaces, I've got it's working, so I'm happy enough. In the old work with Abel Stern, Abel actually went through the trouble of proving that what we were doing there, which I basically just translated from truncated spaces to fuzzy spaces, 1-to-1. But there's no proof for fuzzy spaces that it works. For truncated spaces, there is a proof that it works. Even so, it works is not the same as it necessarily works well. So, but it works, we get pictures, so I am happy enough. And the second problem is if I can figure out how to do something that approximates my non-convex double optimization problem to give me nice states, I'll still at first just get, I'll get random states, which means I'll actually get states, most probably, that are very close together, because for the computer, if it's easy to find one solution at one point, unless I do very, very random inputs, it'll find similar solutions over and over again. And that means if I'm trying to cover the sphere, I mostly have points, say, around the North Pole, and then I have no points on the rest of it, which obviously will not give me a good picture of a sphere. So we need to do something about that. So what we do about that is 2 things. Well, we found that so in the truncated case, we are using embedding embedding maps, which are given with the spectral triple. In the fuzzy space, I found that I can really just throw in the algebra generators. So instead of optimizing over all algebra elements, I'm just doing a sum over my algebra generator squared and my algebra generator, and then square it. And this works as a proxy that if this is minimized, my states behave roughly like points. And the other thing that we do is just, what do you do if you want to distribute stuff equally around a geometry? You add in a little repulsive potential. And this repulsive potential, for relatively moderate values of the coupling constant C, it already smoothes out the distribution quite well. So this is really just, it's a technical addition. In principle, we could also say we reject states that are too close to states that already exist, but it's much easier to make the computer just generate states that are roughly equally distributed. And that's the ingredients that we need to make our states. So, right, I have a little slide to show how this repulsive potential acts. And you can see if my repulsive potential is gone, then these are basically at the same point. So this purple area is just a cut open sphere, and I've made it a projection so that I think I forgot what I was trying to keep equal with the projection, but it's not so important anyways. It's a sphere projection. Look up the Wikipedia article about atlases if you're really interested in how complicated those can get. But you can see that without potential, my states are all very, very close to each other, or more or less at the same spot. Like there's one on that side, and then the others are, since these boundaries are the same, they're all sticking to each other. And already with just a tiny potential, we're doing much, much better. And then for 0.1, which is still not large, it's quite equal. And for 1,000, it's even better. So the repulsive potential works and does what we want. And if we look at how the repulsive potential changes the dispersion is roughly constant for all of these states. So it does what we want it to do. So what we are doing then is really just quite a simple algorithm for generating our states. So we start out with generating a first state and make the set of the first state v0. And then we need to look, generate more states. How long do we generate more states? So what we want is that our states have a dispersion. The dispersion is an area for our sphere, which is two-dimensional. So what we want is that the square root of the area, which is kind of the radius, should be less than the distance. The sum of the square root of the dispersions should be less than the distance between the 2 points, to have the points not be overlapping. So the two states with a dispersion, we want them to not have overlapping dispersion. So the easiest way we actually found to implement this, which here sounds pretty complicated, is the states will anyways distribute themselves evenly around to avoid the repulsion. So that means we can actually just calculate what is the surface area that we expect, what is the dispersion of the states, what is the area of these dispersions, and then divide surface area by area of the states. And that's a good approximation. So until we have as many states as are needed to saturate our geometry, we just find a new locally minimizing vector and append that vector to our set of states with low dispersion. And then we calculate the distance between them. So for this distance, we do the whole optimizing over the algebra. And we run that. It takes depending on the size of the matrix algebra, it takes between like, I get nice pictures for n equal 8, a picture for n equal to 8, which, let's actually go to the next page where I have such a picture. That's a picture that takes about a day. So this is not bad. The problem is the number of states grows very fast with, well, the number of states does not grow fast with the size of the matrices, but the computational complexity grows much faster. The matrix size grows with n squared, because in my Dirac I have n by n matrices, but because the matrices are acting from the left and the right, my Dirac is actually an n square by n square matrix. So that grows by n square for some calculational purposes. And then the algorithms that are applied to this also have a scaling in the matrix size with how long they take. So n equal 8 works very well. For n equal 10, I need to take more than a week of letting it run for my computer to get states. And then I also need to generate a few more states than for n equal 8. But n equal 8 already, you can see this picture. It's a pretty nice picture of a sphere. We've got a bunch of points that are lying quite close to the surface of the sphere. I once upon a time tried getting LaTeX to actually compile a rotating picture of a sphere. I have given up on that. Getting LaTeX to do animations is a little bit of a problem. So I can run the algorithm, I can generate my states and the distance matrix, and then it can use the graph embedding algorithm, which is actually called Smarkov. So the algorithm is called SMACOF, which stands for scaling by majorizing a complicated function. So then I get that picture. And I realize that it's already 5 minutes to 7 and I'm on less than half of my slides. So I will try to speed up a little bit, because the actually interesting part happens now. So I told you about the picture of the sphere. Now I can wonder, what else can I do? And something else that I could do is a deformed sphere. And I deform my sphere by taking the Dirac operator for the sphere. And I just add in, oops, sorry, not IJ. Should call this JK. So you can just add in a new coupling constant here. Just rescale with a real number. And the idea is that maybe if I add this real number to deform my fuzzy sphere, what happens might be something like a fuzzy ellipsoid. So maybe if I have a function here, what happens is something like this. And I'm actually going to restrict myself a little bit more. At first, I have some backup slides with pictures of more general cases, but I'm going to say I put C1, 1. So I'm actually only scaling one of my axes. So the cool thing is, if I do that, I can actually analytically calculate the eigenvalues. I'm going to skip over the analytic eigenvalue calculation because, well, it's long. If you want to see them, ask me later and I write them out. But what we see is that as we deform the eigenvalues, so you can see here the darkest line, that's the undeformed sphere. You have the typical linear fall in the middle, so that's for the two-dimensional happening, and then you have a very strict cutoff here. No more eigenvalues over that. And you see that as you increase the deformation, first you just you're still two-dimensional, but it gets a little bit flatter. And then if you have a very strong deformation, it gets actually quite flat. There's a little bit of a region here, which is roughly two-dimensional, but then here that's maybe more one-dimensional. That looks a lot flatter. So actually what we'll see is this kind of does a cigar shape. With the eigenvalues, I can also look at the spectral variance of the geometry. The spectral variance is a close cousin of the spectral dimension. This is work that John Barrett and his former student Paul Druce and I have done together. And if we look at the spectral variance, just knowing it's a dimension measure which has some dependence on t, where t is a length scale parameter. So for the not deformed case, we can see it's zero dimensional at very short scales. That's where the discreteness, the fuzziness sets in. Then it's two dimensional, and then it slowly falls off towards zero. The slow fall off for the sphere is because the sphere is a compact space, and as we zoom out from the sphere, we slowly don't see the sphere anymore, but only a point. And then we can look at the deformed sphere, where we can see it. We have a two-dimensional region, but then we get lower dimensional region. These are the parts where it no longer really looks like a sphere if we're looking at other scales. But what's really exciting are the new pictures. I'm only flashing. This shows how the dispersion of the states changes with matrix size. It changes with 1 over the matrix size. Then this shows how the state number changes. The state number goes linear with the size of the matrix. The linearity is different for different deformations, but linearization. And now comes a picture that I've been meaning to show you. We've got the round fuzzy sphere, and here is a deformed fuzzy sphere where I have put one of the couplings to 2. Now, obviously, this is a round sphere. Sorry, my headphones just decided to die. Oh, yeah. Sorry, they're plugged into charge and I unplugged them, so they gave up. Can you hear me again? Okay, good. So this is obviously an ellipsoid, and this is actually a best fit ellipsoid to the points. The direction of the ellipsoid is random because my embedding just starts at some point. It doesn't know which point it is. It just puts that point somewhere and then orients all of the other points around it. So it'll start in a random direction. And then I can look at what would I expect for the axis for the deformed fuzzy sphere. And I can see I'd expect with c equal 2, I expect that 2 axes are scaled like 1 over c. And the last axis is not scaled because the other 2 axes are the same as before. And that actually roughly comes out. And the fit is pretty good. So for the round one, clearly the fit does very, very well, and I understand it very well. I'm actually still trying to figure out, because it seems like that's approximately what happens, but maybe not quite. And I'm not sure if my understanding of what exactly my coupling does, so this coupling does to the ellipsoid, if my understanding is missing, or if this is just as good as my fit algorithm can do with the number of points I have. Okay. Now, I can look at how good is this actually? Like, this is a pretty picture, but is it a good embedding? And one way to look at how good the embedding is to say, let's compare the distances as they are in the embedding with the distances as they are calculated beforehand. If the distances would not embed in the space, then there would be a mismatch with this. That could, for example, happen if I tried to embed 2 torus into 3-dimensional space. It does not embed into 3-dimensional space. It would need to be twisted. It would need to be deformed. So it'll not, a flat 2 torus does not embed into 3-dimensional space. It would embed into 4 dimensions or into 2, but I haven't made the torus work yet. But for the deformed sphere, with different deformations, we can see the correlation between the points, the distances in the embedding and the distances as calculated from the algebra. Like 1 would be perfect, and the worst ones are 0.996. So pretty sure this embeds into two-dimensional space, into three-dimensional space as a sphere or a deformed sphere. Great, and that already brings me to my summary slide. I'm sorry I accelerated a little bit in the later part of the talk. Timing when writing is a bit of a problem. So what I hope you took away from my talk today is, what are spectral triples? I've showed you a picture of a spectral triple as derived from using the con distance function. And I've shown you the deformed fuzzy sphere as an example of a very simple spectral triple, where I still have a parameter that I can tune to get different behaviors and different geometries. So something where I can actually test toolkits to understand fuzzy spaces better and have an idea what to expect happening. Well, I've got a lot of future plans working on this, but we'll see where that goes. But I actually have written the code to visualize the fuzzy torus. It's just not working yet. Something about the topology seems to mess with my algorithm, and finding that bug is hard because I'm not quite sure if it's a code bug or a fundamental misunderstanding in the algebra by myself. I'm also working with John on some analytic results about the deformed fuzzy sphere, trying to understand better what it does. And are there any bespoke fuzzy spaces? And I'll go to the thank you slide because I want to add here. So in the computer simulations, we get what we like to call random fuzzy geometries or random finite spectral triples. And in principle, this algorithm should also be able to visualize those. I've done pictures of some. They're not in these slides because I don't understand them yet, because something is happening there that I'm not very sure about. But eventually I will make this work, I hope. And yeah, so thank you for listening to me. And are there any more questions?
So thank you, Elle, for such a visual talk. Does anybody, an interesting talk, does anybody have any questions?
I think visual talk is an apt descriptor.
It is, it's very visual. It's a special treat. Yeah. Well, so I did before this, so this will be a very tangential question, so I hope you don't mind. But I did
at all.
Okay, so I took a look at this older paper, the one that I had linked into, the one that you called older that I called recent.
Yeah.
So in it, you were talking about there's this Gromov-Hausdorff distance that you were using in order to compare metric spaces. And so if I understood correctly, this is basically a distance function that you have, right? A distance function between two metric spaces. So the question I had is, this seems like it might be able to set you up for either like some sort of either a recursive concept, or even you might be able to do an infinite tower of these things. So what I mean is that like a metric space is just a set together with a distance function on it. But you might be able to abstract that where every point in your metric space is itself a metric space, and then you use this distance function. Do you see what I'm saying now?
Yeah, you're thinking about a space of fuzzy spaces.
metric spaces of metric spaces. Exactly. Yeah. Like
Yeah,
metric spaces of metric spaces. And there seems like there's two things that you could do with that. You could either make an infinite tower of these things, or perhaps you could even do it recursively somehow so that it's its own. Have you seen, so my question is basically, have you seen has somebody already done this, or is it a construction that you've seen before?
not that I know of, I think. I mean, on some level, we're kind of implicitly using that, of course, when we're doing the random fuzzy geometries, which are a kind of a path integral over geometries. So
Yes.
we are just using this to get a measure on them, but we haven't really used the distance between them at any point. So yeah, I don't think.
You haven't seen it. I'm sure somebody's, maybe some mathematician somewhere has already thought about it and worked it out. Does anybody else have any other questions? Oh, yes, Jens. Okay.
Hey, yeah, thank you for the human-friendly introduction to spectral triples. You mentioned earlier there is an algorithm that given the pairwise distance of points to approximate a Riemannian geometry. Do you have a name of that algorithm?
Oh yeah, that's the Smaker.
Oh, okay. Okay.
So
the one with the funny name.
Sorry. Oh. I went too far. These are my backup slides with more pictures of deformed spheres. I might as well flash them at you.
Yeah. Okay.
Yeah.
Okay, that's the one. Okay, thanks. Yeah, I'm curious then.
Yeah, this was Abel Stern, whom I worked with on this. Found that algorithm and made it all work. I was a pleasure to work with a student who was just doing a lot of the stuff.
Okay, cool.
With yeah.
What programming language are you using? May I ask, or what tooling?
So this project, the code is actually Python, and the code for the old paper with Abel is on GitHub.
Okay.
The reference is in the paper. You are very welcome to take it and run with it. And if you are trying to run with it and have any questions, please drop me an email.
Check it out. It would be. It's fun. It looks like fun. Thank you.
Okay, so John Barrett has a question.
Hi, just on that last slide, well, before the conclusion slide, you showed the dispersion for all different size matrices. Yeah. So.
Oh wait, this okay.
Yeah. So that. Wait, what is on the bottom? Oh, bottom. It's not different size.
No, it's not different. No. This is the correlation coefficient for different deformations.
Yeah, excuse me. Yeah.
So this is a goodness of embedding measure that I made up. And I mean, yes, you already saw that it's a bit of a dispersion, as in I've plotted the average, but I also plotted each single point just to give us an idea of how far they spread. And mostly they don't spread very far.
Right. Okay, so why is the one for c equals 5 much better than the others? Is that just some sort of scaling thing, or is that a real?
The c equal 5 actually just has a much easier time. As you deform the geometry more and more, it gets more cigar shaped, and the surface area of a cigar is smaller than of a sphere, which means c equal 5 has considerably fewer points on it than c equal to 1. And with fewer points, it's easier to embed them.
Oh, I see. Right.
So that's why this one is doing much better. I'm not sure why 2.0 is not doing better than, but there's a lot of moving parts in there, picking them all apart. Also didn't seem worth it considering that they are all doing pretty amazing. If I found correlations like this in an actual measurement and not in a goodness measure, and an actual measurement correlations like that would be highly suspicious.
Okay, so Francis has got a question here. I'm going to unmute you. Go ahead, Francis.
Thank you very much. So I wanted to ask, I noticed that in your slides, you showed us that there is a polymetrics that is included in your parameterizations of your spectral triples.
Yes.
With that case, is it possible that we can extend the results to Jordan algebras because of the unimodular nature of these algebras?
So I am not sure about extending like non-commutative geometry to non-associate geometry for the geometric part. I don't know anything about, but for one of the interesting results in non-commutative geometry is a non-commutative standard model where you can, and John actually worked on that too, where you put together all of the particle content and use a finite algebra, and you get all of the particle content and the Higgs, and it all makes a wonderful story. And for that, there actually is a version using the Jordan algebra, making it a non-associative standard model. So that might be possible. And that is work by, I always forget his name. He's at PI.
Latham Boyle and Shane
Exactly.
Farnsworth.
Yes, thank you.
Okay. And finally, I wanted to know, did you encounter any problem with mass gap in your simulation?
Nothing has a mass, so no, there's no mass gap.
Not even the Dirac that you used?
No, it's the Dirac that is associated to the geometry. We haven't really added in matter. Adding in matter would be at some future point, and then maybe then we would see that. But so far, pure geometry is more than enough complication.
Okay, so Anwasha has a question. I'm just going to unmute you. Go ahead.
Hi, thank you for the nice talk. I have a question with your earlier slides where you had introduced the spectral triple for a fuzzy sphere, the ADH. So I just want to clarify that I presume the Dirac operator you wrote, that just boils down to the Glaser-Schneider Dirac operator after some simplification. Is that right?
Kind of. It's if I call the Glaser-Schneider operator little d, for example, then what this is actually it's two copies of the Glaser-Schneider operator.
Okay.
Positive and a negative one, and this has, amongst other things, this makes the spectrum symmetric because, as you probably know, if you have the Glaser-Schneider, you have the largest eigenvalue appears, and then the smallest there is no smallest eigenvalue that is negative of the largest eigenvalue, and the doubling makes that happen, and it also does the KO dimension nicer. So.
And one more question is that can you write down the chirality operator or real structure operator in this setting with this spectral triple ADH?
Okay, let me see if I have copied it out. If I haven't copied it out, then this is I haven't copied it out, and I don't know it by heart right now. I think I think the chirality is really just gamma 0, but I'm not sure.
Okay.
Maybe John can help me out, but
Well, he hasn't come to your rescue yet.
yeah.
Okay. Do we have any more questions? Yeah, go ahead.
No, it is actually in John's paper. He has written this out explicitly for that case. So.
Okay, the Journal of Mathematical Physics paper, right?
Yes.
Yeah, I will see. Thank you.
So,
oh, here he is.
Okay.
Go ahead, John.
Yeah, you just need to unmute me. Yeah, sure. Well, the chirality is just the product of all the gamma matrices as normal. and the real structure is basically Hermitian conjugation of the matrices and the usual charge conjugation for the spinors.
Okay.
So it's quite straightforward.
Okay. Thank you.
You're welcome.
Do we have any more questions? Well, now might be a good time to close things off. So thank you again so much, Elle, for giving such a stimulating and again, very visual talk. Thank you to everybody for showing up and for your questions. Our next talk is scheduled in just 1 week on the 27th of March, 4 p.m. Berlin time. So that's 2 hours earlier than usual. We have Professor Balachandran from Syracuse University speaking for us on spin half from gluons and a little more. So thank you again, Elle, for giving us such an engaging talk. And thank you to everybody for showing up. We look forward to seeing you next time.
Well, thank you for inviting me and organizing this really interesting series. So
my pleasure. Yeah, thanks again.